Hi everybody. So in today's video what we're going to talk about is phase equilibrium in two component systems. Why on earth would we be interested in that? Well, one reason we're interested in that is how do we typically control the properties of materials? We control them by mixing different materials together. So in a two component system, you've got two distinct materials, and our goal is to understand when they're in equilibrium, that is when they will mix, and when they won't mix. And if you look around you, I'll give you a couple of examples in a second, but if you look around you, mixtures are everywhere. And so one thing, alcoholic beverages like wine, it's a mixture of alcohol or ethanol and water and some other things. Steel, what is steel and other alloys? Well, it's a mixture of multiple elements. So steel is iron and carbon and vanadium and all these other elements combined, which give it certain mechanical properties, and you see it all around you. Now, the same thing is true with polymers. We can make alloys of polymers, or at least in principle, we can make alloys of polymers, and this would allow us to maybe tune the mechanical properties of our material. So a prime example that I like to give is the soles of your shoes. And so if you were to look at your options for different polymers when it comes to making the soles of your shoes, well, there's a lot of them, right? Turns out that one component of the material that makes up the soles of your shoes is polystyrene. And so here's a lid from my coffee cup. You can kind of see what this material is like. I mean, this is not a great material to have for the soles of your shoes. What might be? Well, things like polybutadiene could be good. It has this rubbery character, but it doesn't have quite the strength that we would want for a material like that. So if you were to zoom in on the soles of your shoes and look at what the structure of that material is, what you would find is you've got little spherical domains that are distributed throughout the material. And these are the hard polystyrene parts. And they give that strong, or they impart some strong mechanical properties to the material, but you also want them flexible and rubbery. And so these hard polystyrene inclusions are linked together by polybutadiene chains. So this is a little bit different though. This is not quite a mixture. We had to play some funny tricks to get this to happen. So what these materials look like are like these tri-block copolymers, where you have three distinct chemical blocks. So this, for example, might be your polystyrene block, and these might be your polybutadiene blocks. So we've gone through a lot of trouble to link these polymers together and to make a useful material. Why do we have to do this? Why is it that we had to make a tri-block copolymer to get a nice organized material like this? That's what we're going to talk about today. Okay, so phase equilibrium. What does that mean? Well, let me give you a couple more examples. I have some water here. And so let me take this material and just add a little bit of food coloring to it. And you can see what's happening, right? Probably shouldn't have picked green since I have a green screen, but hopefully I'm in front of it so you can see it. So you can see that the dye is spreading out through the water. Why is it spreading out like this? It's spreading out like that because of entropy. So entropy wants things to mix together. And today what we're going to focus on is only the entropic part of what's going on. Now compare that, or contrast that, to the case of mixing these two substances together. This is water still. And in the other test tube that I'm pouring in right now, I've got oil. And hopefully, if I move my hand, you can see, and of course you know this from everyday experience, but you can see the oil layer is here and the water layer is here. So you've got two kind of related problems. On one hand, entropy wants things to mix. Entropy is going to be the driving force to get multiple components to exist in a mixed up state. But you can see from the oil that there are other things that prevent that from happening. And in this case, that's going to be interactions, which we'll talk about in the next video. Okay, so let me move my test tubes out of the way. Hopefully I don't knock them over. And let's start to figure out what we're going to describe here. So let's start by thinking about phase equilibrium in a one-component system. And we've already done this. What was that? Well, when we did that, we had something like, let me just draw a system like this. And I'll just kind of put this artificial divider down the middle. Phase equilibrium in a one-component system is between, well, different phases of a substance. So you might have, for example, water as ice, and then you might have water as a liquid. Now, phase equilibrium is telling me how these things are coexisting with each other. So if I was to look at this system at a temperature of 0 degrees at normal pressures, well, what you would expect is that you would have both of these phases. You wouldn't have ice, you wouldn't just have liquid water, you would have both water and ice if you are exactly at 0 degrees C. So what that means is that the chemical potential of the ice is going to be equal to the chemical potential of the liquid. So there's no real benefit for ice to move into the water phase or for liquid water to move into the ice phase. In other words, it can do this. A particle can move from the solid phase to the liquid phase, but at the same time, you're going to also be getting water moving from the liquid phase to the ice phase because the chemical potentials are equal. And if you remember what the chemical potential is it's the partial derivative of your free energy, so maybe the Gibbs free energy, with respect to the number of particles. So if I want to see what the chemical potential of the ice is, then that would be equal to the partial derivative of the free energy with respect to the number of ice particles, holding all this stuff constant. Or in the language that we use in this course, it would also be equal to the partial derivative of the Helmholtz free energy, again, constant volume type systems, with respect, for example, to the number of ice particles, holding all that stuff constant, and that would be equal to the chemical potential of the ice. And it is also going to be equal to the molar free energy of the ice. So remember that chemical potential and molar free energies have the same expression, but we tend to use chemical potentials when we talk about something moving from one state to another state and vice versa, right? But they're the same thing. This derivative is telling me that the chemical potential is how much the free energy changes when I add or remove a particle. So if I consider this example that I started with, if the chemical potentials are equal between the phases, then the free energy of the system will remain the same if a particle moves from the ice phase to the liquid phase and vice versa, because the free energy of the particle in those different phases is the same. So you get equilibrium if the chemical potential of the one phase is equal to the chemical potential of the other phase. So I have ice and liquid as my subscripts here, but maybe a better way to say it is if mu1 is equal to mu2. Another way of saying this is that delta G, the change in the free energy of the system, so another thing, delta G or delta F will be 0 if a particle moves from one phase to another, whether it goes from the ice phase to the liquid phase or vice versa. So in other words, the free energy of my system is not going to change when I'm in equilibrium. So those are important concepts that still apply when we have multiple component systems. So the same thing is true. If I've got a system like this, let's analyze it. Will it mix or will it not? Well, let's compare. Let me first move this to the other side. So this is my system initially. So the state that I'm going to compare to, this will be the unmixed state. And you can think of it, maybe I have a bunch of blue particles. That's going to be one of the types of particles. So it's not going to be phases necessarily. And in this case, it's going to be different substances. So different distinct chemical substances. So in the unmixed state, I'm going to have something like this. You can think of it like this, or if you want to think of it differently, you can also think of it as maybe two distinct unmixed systems. Okay? Either one is going to get you the same thing. And then what I'm going to do is I want to see if they're going to mix or not. So the system in the mixed state looks exactly like what you think it would look like. So in the mixed state, I'm going to have a nice even distribution. Let me just draw a couple in here. I'm going to have a nice distribution of these particles throughout the system, and it's going to look nice and evenly mixed, just like this is now. All right. So that's the goal. So is this going to happen or is this not going to happen? I don't know. Entropy says it should happen, but I just showed you a test tube with water and oil that didn't mix. So sometimes it's not going to happen. So what I need to do is I need to see what is delta F for mixing. So what is the change in the Helmholtz free energy in going from the unmixed state to the mixed state? Or similarly, depending on the situation. So if I'm developing a theory, the Helmholtz free energy is probably going to work a little better for me. If I'm doing an experiment, I'm also interested in what is delta G for mixing. And the equations are going to be the same. Okay, so sometimes experimentally I'm concerned about whether my two polymers will mix. Well, that will be given by the Gibbs free energy, the change in the Gibbs free energy upon mixing, and the same thing for the theory side. Okay. So you already know what's going to happen with the free energies, right? Because if delta F of mixing is less than 0, then that means that the free energy of the mixed state has a lower free energy, or is lower than the free energy of the unmixed state. So I guess I should also say, for completeness, the reverse is true. If it's greater than 0, let's see, less than 0, it will mix. Greater than 0, it will not mix. And if you prepare it in a mixed state, i.e. you shake up the bottle of salad dressing, then you'll find that your system will demix. And there's many different ways that it can demix, and we'll talk about those in an upcoming video. So clearly our job here is just to figure out, well, what is the free energy change upon mixing? So to do that, we're just going to have to write down what these things are for the mixed and the unmixed states, right? Because the free energy of mixing, it's going to be just like Hess's law, right? It's going to be the free energy of the mixed state minus the free energy of the unmixed state. We have to figure this out. So let's start simple. Let's start by saying that there are no preferential interactions. What does that mean? Well, it means that if I have no preferential interactions, it means that the strength of a blue-blue interaction, we can call this maybe an AA interaction. These are A particles. These are B particles. The strength of an AA interaction will be the same strength as a BB interaction, which will be the same strength as an AB interaction. So from an energetic standpoint, a blue particle doesn't care whether it's surrounded by red particles, blue particles, or a mixture, because the energetics, the strength of the interactions between them, are the same. So that means that we're just going to focus in this video on entropy. And what does entropy do? What does entropy say about whether something will mix or not mix? You kind of already know the answer, right? Entropy is going to encourage things to mix because you're going to get a more mixed up, disordered state. It's more likely that you're going to have red particles and blue particles all mixed up than it is to have them completely separated. Of course, there is a finite chance that they can be separated like this. But if you were to look at the system every second for the next million years, these states where things are mixed up are going to be much more likely. So that's another way of saying that entropy is preferring the mixed up state than the unmixed state. That's all that is. So we have to calculate the entropy. So we're going to have to calculate the entropy in the mixed state, and we will have to calculate the entropy in the unmixed state. How might we do that? Well, doing something like this is not going to work. What the hell is DQ? Dairy Queen. What the hell is DQ for an unmixed state or a mixed state? I have no idea. Okay, so while this kind of expression is useful in normal thermodynamics, the Clausius relation, it's not helpful here for describing mixing. It's more helpful in talking about heat exchanging and stuff like that, gases and stuff. But we have another expression, right? Because Boltzmann entropy is pretty easy to calculate. And it's what? Well, it's basically a measure of the number of microstates that you have. So if you don't remember from last semester, this is the number of microstates. And before we go any further, I'll just remind you that this expression is the same one that we use to figure out what the size of an ideal polymer chain is. Because it's just entirely based on entropy. That's why the chain scale is n to the 1/2 power. How did we get that? We counted the number of ways that we can rearrange monomers in a polymer chain, and that was it. And then we got what the size was. So this is useful, and if we want to use it, all we really have to do is figure out how to count the number of microstates in my system. So let's do that. And the way that we'll do this is we will take a lattice approach, or we will construct a lattice model. Because it's going to help us count things. Once you do this, it doesn't have to be done on a lattice. So once you do this, you can generalize it, and you're going to see that it's not going to really depend on whether there's a lattice or not. But let's do it that way because it's going to allow you and I to count how many ways I can arrange things. And how many ways I can arrange things is going to be the number of microstates. Log of the number of microstates multiplied by Boltzmann's constant will give me the entropy. Okay, so again, my goal is to find omega. This is the number of microstates. And it's really, again, just a count of the number of ways I can rearrange the particles. So how many ways? Oops. Come on, my core. How many ways can I, let's not say rearrange, let's say how many ways can I arrange the particles? Okay, so that's a good way of thinking about that. Well, let's do it. So let's make our lattice. And I think that you're going to see why I construct the lattice when I do this. So here's my lattice. And all this lattice is a bunch of spaces where I can put things. So how many spaces do I have here? I've got 1, 2, 3, 4. I've got 20 spaces. So let's say that I've got one particle. And I want to figure out how many ways can I place that one particle in the system? Well, we can count. I could put it here. Let's see. I could put it here. Or I could put it there. I could put it there. Put it there. And I could keep counting. How many different ways can I put the particle in the system? Put it 20 ways. So there are 20 ways to arrange this particle. So that's the game I'm going to play. I'm going to count how many ways I can put things into the system. So That's it. That's all I'm going to do. So let's define some things that will make my life a little easier. First of all, let's define the volume of the A component. So the volume of the A component is going to be, actually, let's not do that first. I should probably tell you what I'm doing first. So let's call the red particles, what do we call them up here? We call the red particles B. So these are B particles. And let's make a blue particle. Make you a little bigger. Oops. Okay. And here's the other one. This will be the A particle. Okay, so now we can define some things. So let's call, let's see. What's the total volume of A going to be? This is the total volume of A. What will it be? Well, let's say that I've got a certain number of A particles and every A particle has a certain volume. So then the total volume of A will be the number of particles that I have times the volume of one particle. That's easy. And let's do the same thing for B. So the total volume of B that I'm going to have will be the same thing. Let's assume that all particles have the same size. So a single particle, A or B, will have volume V0. So this also has volume V0. So the particles are going to have the same volumes, but I could have a different number. So I could have more A than B or something like that. So that's why we're calculating this. So the total volume of B will be the number of B particles that I have times the volume of one B particle. Okay. What else can I say? I could say that I could calculate the volume of my system, right? The volume of my system will be the volume of the A particles plus the volume of the B particles. That'll be useful. And I'm just going to circle these things that are important for us because we're going to use these. What else could we talk about? We could talk, how about the volume fraction? So the volume fraction of A will be the volume of A divided by the volume of the system. So the volume of A divided by the volume of A plus the volume of B, kind of like the mole fraction. And so the same thing for the volume fraction of B, VB over VA plus VB. And because the volume fractions have to add up to 1, right? You have to have 100% of your stuff. Then the volume fraction of B can also be written as 1 minus the volume fraction of A. So we've got this defined, and we'll just use this for the volume fraction of B. All right. So I think we have everything put in place right now to start calculating this. So let me ask you a question. Think about it. So the question I want to ask you is, if you have Na particles of A and Nb particles of B, and you combine them, will they mix? Probably. Think about a thing of Skittles. If you separate out the green Skittles and the red Skittles and you shake them up, they're going to mix, right? So yeah, the answer to this is yes. But when are they going to mix? Well, we're not going to talk about interactions right now. So we're going to say for this video only, they will only mix if the strength of the interaction between A particles is equal to the strength of the interaction between B particles, which is equal to the strength of the interaction between A and B particles. Okay, so this is going to be a condition. So this is what our intuition is telling us. So again, how do we know if we're on the right track when we're coming up with these theories? Well, when we get to the end, they'd better agree with both what happens and what we kind of expect based on our intuition. If we get to the bottom of this and our equation says, no, they aren't going to mix, well, that's just wrong because we know it's wrong, right? Alrighty. So let me scroll down my notes. Okay, so we saw up here that the number of ways that I can put a single particle into the system is going to be, basically, there are always going to be n ways. And because I'm already talking about NA and NB, let's just say that there are n ways to place one particle. So I can do that. Okay. So then what is the entropy of the mixed state? Let's do that part first. Well, let's do it this way. Let's say that this is my lattice. All right, so I've got what, 16 now? So this is, let's say that this is the unmixed state, because we'll come back to it. And then this, of course, will be the mixed state. I'm going to ask you the question that I have already asked and answered, and that is, how many ways can I place one particle in the mixed state? N, right? So there are n ways. Let me write mixed. And I'll also say n ways per particle. So then we can just calculate what we expect the entropy to be. The entropy then of the mixed state is Kb log of n. And just to remind you, this is only for one particle. So we're just talking about one particle right now. Okay, so let me draw what the mixed state might look like. Let's just assume that I have equal numbers of A and B particles. So the mixed state, I'm going to have 8. So 1, 2, 3, 4, 5, 6, 7, I don't know, 8. That's where my 8 A particles are going to be. And then every place else, or every other place, will be where my B particles are. Now, what would happen if it was unmixed? Well, if it was unmixed, you would get something that looks like this. Right? The two are going to separate from each other. So really what's happening in the unmixed state is that you're confining your particles to a fraction of the system. And in this case, it's half the system because I have equal numbers of A and B particles. So if the entropy of the mixed state is Kb log n, what is the entropy of the unmixed state going to be? Well, I still have n spaces on the lattice, but I'm not able to put a particle in all of them, right? I'm only going to be able to access some fraction of them. And in this case, phi A, the way I've drawn it, is 0.5. And so phi b is 0.5. So we can just count. So you can see in the area of the lattice where I've boxed it in with that yellow box, there, instead of there being 16 spaces, there's only 8 available. So the number of spaces that I have that are accessible in here, the number of spaces for B is what? Well, it's some fraction of the total number of spaces, and it's actually going to be phi b times the number of spaces. And in this example, it's half of them. So there's 16 spaces that I could put the particle in the mixed state. In the unmixed state, there's only going to be 8. And so the same is true. I apologize, there's a lot of NAs here. But this is the number of spaces that I can put an A or a B particle. Okay? So I have the expression for the entropy of the mixed state. Now I just need to come up with the entropy for the unmixed state. And there's going to be 2 contributions. So the unmixed state will be KB times how many spaces there are available for A. So it'll be times the logarithm of phi A times N. And then what else? Well, I also have B particles. So this will be plus KB log of phi B times N. And again, this is per particle. You know what? Maybe I should... It'll work this way, but I'm going to erase this and break it up into 2 components so that I'm not going to skip any step. So I'll say the entropy of A in the unmixed state will be KB log of phi A times N, and the entropy of B in the unmixed state is going to be KB log phi B times N. Okay, so let's do this one step at a time. What is going to be delta S for mixing for A particles? Well, Hess's law tells me it's the entropy of the final state, the mixed state, minus the entropy of the unmixed state. So for A, this is going to be KB log of N, that's going to be the mixed state, minus KB log of phi A times N. So again, this is mixed. And that's unmixed. Same thing for B. So delta S mixing for particle B will be the mixed state, KB log N minus KB log of phi B times N. So before we go any further, let's just simplify this. I mean, these expressions look the same, so this will apply to both of them. Let's just take A, delta S mixing, we have logarithms involved. So the logarithm of a product is going to be the sum of the logarithms. So this will be KB log of N minus KB log of phi A minus KB log of N. Sweet. Things cancel. I like that. So the change in entropy for the A particles, for a single A particle, I should say, in going from an unmixed to a mixed state, will be minus KB times the log of its volume fraction. That's good. And we could do the same thing for B. Delta S mixing for one single B particle, only one particle, is KB log N minus KB log of phi B times N. And so we play the exact same game that we just did. We have logarithms, so we can simplify this expression, and we'll get minus KB times the logarithm of phi b. And that's that. So now what? Well, this was only for one particle, and I can't state that enough. This only for one particle. So we need to do it for all the particles. So the total change in entropy, for mixing is going to be the number of A particles times the change in entropy for a single A particle. So that was this. So number of A particles times minus KB log of phi A. That takes care of the A component. And then plus NB times how much the entropy changes for a single B particle to be mixed. Okay. All right. So if I simplify this, what I'm going to end up with is that delta S for mixing is going to be minus KB times NA log of phi A plus NB log of phi B. Fantastic. Can I simplify this a little bit? Sure. But I can do more than that. I can also get the free energy from this. So let's get the free energy first and then see if we can simplify this expression a little bit to get something that we like. Maybe that's a little bit more useful to us. Well, what is delta F of mixing? Think back. What's the definition of the Helmholtz free energy? It's going to be the change in the internal energy for mixing, and then minus T times delta S of mixing. So what's this term? That term is 0. Why is it 0? It is 0 because there were no preferential interactions. A particles don't care who they're surrounded by, and the same for B. So delta U mixing is 0 because there are no preferential interactions. Great. So that means then that the free energy of mixing is just going to be minus T times delta S of mixing. We already did that. So delta F of mixing is going to be plus KBT. That's our thermal energy scale. Multiplied by NA log of phi A plus NB log of phi B. And you can check yourself. I mean, it's trivial, but you could prove to yourself that delta S of mixing is going to be minus the derivative of delta F mix with respect to temperature, holding everything else constant. All right, so that's a good self-check. That's why we spend time learning Maxwell relations. Before I go on, what if I wanted to do delta G instead of delta F? Well, delta G mixing will be delta H mixing minus T delta S mixing. So you've got enthalpy now instead of internal energy. So what do we do? Well, enthalpy is still going to be related to interactions. So you can prove, and we'll see it in a little bit, that if there are no preferential interactions, then the enthalpy is not going to change either. You can use the Gibbs-Helmholtz equation to do that. So if that's the case, if you don't have preferential interactions, then delta G of mixing will still be T delta S of mixing, and you're going to get the same thing. You're going to get that delta G of mixing is KBT NA log phi A plus NB log phi B. So you're going to hear me refer to this a lot. When I write down the expression like this, this will be the entropic contribution to the free energy. So I'm going to keep saying that. Well, entropy is doing this, but something else is doing something else, okay? So when I say the entropic component, that's what I mean, this part that I've highlighted. Okay, so can I get this in a different form? Well, yes, I can. What if I, how do I want to do this? Let's divide by something. Look what I've got here. I've got capital NA, capital NB. So what I could do is I could write that delta F of mixing divided by the total number of particles will be KBT times phi A log of phi A plus phi B log of phi B. How does that work? Well, if I divide through by n, let me just write it here. If I divide by n, which is n, the number of A particles plus the number of B particles, then I'm going to get something like a mole fraction. So Na divided by n is actually the mole fraction of A. But I could multiply the numerator and denominator by the volume of a single particle. And so if I do that, I mean, this is just 1, but it will be the same. It will give me the volume fraction of A. So that's why I get the phi A coming out front. So this is important. This is the change in free energy per particle. So this is the free energy of mixing per particle. So you could write it different ways. You could write it per mole if you wanted. You could write delta F mixing per mole. And instead you could write that as RT phi A log phi A plus phi B log phi B. So I tell you this just because you're going to see it in different forms, and depending on what it is you're trying to calculate, you're going to have to use the correct form, all right? Okay. So that's it. That's the first real component. Now let's take a look at it and see if this makes sense to us. So let's write delta F of mixing per n as delta F mixing with a bar on top. Okay, it's like a molar free energy of mixing. So that will be KBT phi A log phi A plus phi B log phi B. And where did we start this conversation? We asked the question, if I mix these two things together, or I should say if I combine these two things together, will they mix or will they demix? That was the question I asked. Remember that this expression is due to entropy. And you and I, well, I certainly did, I hope you did, reasoned that entropy will cause things to mix together. So entropy will favor mixing. Well, if that's true, if this is going to mix, this had better be less than 0 if they are to mix. Is that true? Certainly looks true to me. How did I know that? Well, phi A has to be between 0 and 1. Right? It's the volume fraction. It's either 1, 100%, or it's 0, 0%. That's all it can be. Similarly, phi B has to be between 0 and 1 for the same reason. So that means this is between 0 and 1, that's between 0 and 1, and the same thing here. Okay, what is the log of phi A going to be? Well, if phi A is between 0 and 1, the logarithm is negative. Right? So if I was to plot the logarithm, the natural logarithm, this is phi, let's not do that. Let's call this x, and this is log of x, and this is 0. The logarithm function, the natural logarithm, kind of looks like this. And this point is 1. So in our function, we're always in this region here. Okay, and the natural log goes to minus infinity at 0. So we're always going to be negative. It's guaranteed that we'll be negative. So that means that this term is less than 0. That term is less than 0. So at least according to entropy, if there's no preferential interactions in the system, the free energy of mixing is going to be due only to entropy. Well, according to that, then things will always mix together. So that's fantastic. That's exactly what we expected. Okay, so we have a bit of a problem, though. Have I said anything about polymers yet? Well, I mean, other than introducing this video, no. Nothing that I've done so far really depends on polymers. So this expression, as I've given it here, is only valid for small molecules. Or I shouldn't say small particles, or what I should actually say is that it's only valid for non-bonded particles. So atoms, molecules, like single small molecules, grains of sand, Skittles, beer nuts, whatever, right? Things that aren't bonded to each other. In the case of the polymers, we have a problem because the monomers are linked to each other. So in terms of our lattice, that's going to put constraints on where these things can be because these particles are linked like this. The same thing for the blue. You can see that if I have a polymer, they could be linked like that, but the monomers have to be in adjacent lattice sites to each other. So if I want to change this expression, then I need to basically correct for the fact that I don't have Na particles. So for polymers, when I originally wrote this expression like this, that's how many particles I had. But the number of polymer chains I'm going to have will be smaller, right? It's going to be the number of particles divided by the degree of polymerization of the chain. Let me draw it out just to be absolutely clear. If I have my lattice like this, then let's use lowercase a, otherwise it's going to look a little confusing. So little na is the number of particles I have. So I could put them, let's say that I have something like this. So in this case, I've got 6 particles. But what if now I have polymer chains with a degree of polymerization 3? So let's call capital Na the degree of polymerization of A. Okay, well, if I've got, and in this case, let me just say it, capital Na is equal to 3, then it should be pretty obvious that for a polymer, the number of polymer chains that I have, so the number of chains, will be little na divided by the degree of polymerization, capital Na. So you can see for this example, that will give me 2 polymer chains, and you can count them. Here's one polymer chain. There's the other polymer chain. So this is why I go through the math, because we're going to have to correct this expression now. We have to take into account, let's say in this expression right here, that the number of A particles, and yeah, here it's capital Na, but this is why you have to think and read into what your equations are telling you. The number of A particles will not just be this, it'll be this number Na divided by the degree of polymerization. So you can see that that's going to change our expression. We're going to have to divide phi A and phi B by the length of the chain so that we get the proper balancing of those terms. So that's what we do. Delta F of mixing, put the bar on top, per particle, will be kBt times phi A over Na log of phi A plus phi B divided by Nb log of phi B. And because I've been putting Na and Nb all over the place, let me be really specific about what these terms are in this equation. In this equation, this is the degree of polymerization of A. This is the degree of polymerization of B. This is the volume fraction of A. Oops. This is the volume fraction of B. Okay? Keep that straight. I know I had a lot of things in there, but just think about what it means. That term in front is how many particles I have. This is how many ways I can rearrange them. So that's why I divided by the degree of polymerization. So last thing I want to talk about, we saw that in this expression up here, that this was only valid for non-bonded particles. And we saw that it gave a value that was always less than 0 for the free energy of mixing. In other words, entropy was always driving things that were not bonded to mixing, excluding interactions, right? We're not talking about interactions. Well, what happens in the case of a polymer? Well, let's consider a polymer. Let's consider ultra-high molecular weight polyethylene. So these are used in implants, so hip joints and things like that. Really super high molecular weight. Well, if you have high molecular weight, what does that mean in terms of the degrees of polymerization? It means the degree of polymerization is much, much bigger than 1. In other words, it's huge AF. Same thing for B. Okay, so if B is really big, then this is also huge AF. What does that do to our free energy now when you have polymers? Well, let's look at the limit as Na goes to infinity, Nb goes to infinity, of delta F of mixing. Well, you're going to get kBt up front. Phi A, I'll just put in the infinity, log of phi A plus phi B. Phi B hopefully you see what's going to happen. That term will go to 0, and that term will go to 0. So you can see that entropy does not help polymers mix. It's negligible. So another way of saying this is that the entropy of mixing for polymers scales as 1 over n, where again, this is the degree of polymerization of my chain. So you can see that for very large n, for large capital N, the entropy of mixing is essentially 0. So that's problematic because it was entropy that's causing these things to mix together. And if entropy is about 0, it means that your interactions are going to play like a really big role. So for polymers, interactions are the most important thing. So interactions, I should say, dictate the phase behavior. Okay, so let me one last time write down this equation and then we'll end. This is it for today. The change in free energy upon mixing, in other words, the free energy of mixing, is equal to kBt phi A for the degree of polymerization of A, log phi A. And instead of writing phi B, let's just write 1 minus phi A, right? Let's reduce the number of variables that we have. So this is plus 1 minus phi A over NB, log of 1 minus phi A. Couple comments. This is only due to entropy. We'll talk about interactions in the next video. If you have a solvent or a small molecule, so if you have solvent or small molecule, I hope it goes without saying, but the degree of polymerization of a small molecule, whichever it is, whether it's A or B, that will be equal to 1. So you're going to have to make that simplification in your expression for the free energy depending on whether you have two polymers that you're mixing together, or whether you have a polymer and a solvent, or if you just have two solvents together. Okay. So that's that. That's where I'm going to end today. So what have we seen? We see that when we have two components that are in a system, entropy tends to favor them mixing. So if they mix together, you're always going to increase the entropy, at least if you have small molecules, things that don't have monomers bonded to each other. What we've also seen is that when you have a polymer chain, because you've linked up the monomers like this, the result of that is that if you have a really, really, really high molecular weight, the change in free energy for mixing is 0. So it's not really favoring mixing. It's also not, it's not opposed to mixing. It's just there's no benefit to it. And that is because the entropy of mixing is 0. So where do we go from here? Well, it's clear, even if you just go back and look at this oil and vinegar example, or oil and water, here's the oil, here's the water. It's clear that this picture of the free energy is not describing everything. Because things sometimes mix, they usually mix, but things sometimes don't mix. So we're going to have to include interactions in our expression if we want to account for that behavior. So the next step is to include interactions that are preferential. And that's going to completely change the phase behavior, and it's really going to distinguish the phase behavior of multiple polymers that are in a system from the phase behavior of traditional things like small molecules. So again, just linking up the monomers completely changes everything. So that's what we're going to do next. And we'll see what that does in terms of the free energy. And it complicates things, but it also gets much more interesting, and it provides us with ideas of strategies to get things to mix together. One example of that was the tri-block copolymer I showed you. So we will talk about that, but we really have to just develop this formalism first so that we have an expression that we can utilize to predict whether things will mix together or whether they won't.